homework for this section, our goal here is to find the volume using the disk method. The formula that we're given says that the volume is equal to pi times the integral from a to b of r of x to be squared dx. Or if it's the so-called washer method, the volume is pi times the integral from ab of capital R of x to be squared minus little r of x to be squared. Let's consider this problem. We'll do part A first. Here it says about the x-axis. So the graph of the square root of x looks like that. And here it says y equals 0, which is the x-axis, and then x equal to 3. It stays there. You want to rotate this about the x-axis, so it's going to spin along the x-axis. Now, if that be the case, then we say that the rectangular slice for the radius is perpendicular to the axis of revolution. The thickness of the radius, look at that, is with respect, is parallel, or it runs with the x-axis. So the thickness is with respect to x, or dx. So now we calculate r of x, and it's r of x because we're using dx. So r of x is equal to the curve itself, the curve minus the base. We use the area formula from the previous section, the upper function minus the bottom. So here this is the square root of x minus 0, just the square root of x. Now, looking at this in its full sense, we have this shape of the disk. So the volume is equal to pi. We're integrating from 0 here to 3. So from 0 to 3. This is the radius to be squared, just the square root of x, to be squared dx. So here, this is pi times the integral from 0 to 3 of x dx. And here we get pi times x squared all over 2. And we evaluate that from 0 to 3. And so the volume is 9 pi all over 2. Part B, find the volume about the y-axis. So examining this, remember the curve, the basic shape that we have is this, but to evaluate this about the y-axis means that we have symmetry about the y-axis. So it's actually doing this. in the solid region, and you see the hole there. So if that be the case, now what I'm going to do is just come over here and just draw the part that we can catch. X-axis, the y-axis. And since we're rotating this about the y-axis, draw that a little bit better so you can see it. So here, notice that we have a hole. See that hole right here? We have to get rid of that. So we use the washer method. Right? So we have the big radius slice, which includes everything. Its thickness is dy. The thickness runs with the y-axis. So here we'll be able to find big R of y. And then now we need the hole, the area that we want to get rid of. We take another slice, and this is little r of y. Well, this shape goes to 3, and so since we're solving this with respect to y, we started with y equal to the square root of x. If you solve for x, you get x is equal to y squared. So we have to use this equation when we're calculating the radius with respect to y. So capital R of y is 3 there. And then little r of y is the curve. And the curve here is y squared. Now, if x is 3, then with respect to y, then that means that y is the square root of 3. So we're evaluating here from 0 to the square root of 3 for y. So we set this volume equation up. The volume is pi times the integral from 0 to the square root of 3. Capital R of y, that's 3 squared, minus little r of y, that's y squared, to b squared dy. So this is pi, simplify that, the integral from 0 to the square root of 3. This is 9 minus y to the 4th dy. Mercy. I do not like these electronic pens. This is 1 to the 4th dy. So now we integrate, we get pi times 9y minus y to the 5th all over 5. Evaluate that from 0 to the square root of 3. So that gives us, this is pi times 9 times the square root of 3 minus the square root of 3 to the 5th, which is 3 times 3 is 9 times the square root of 3 all over 5. minus 0, and you get 0 and 0. So this gives us 36 pi times the square root of 3 all over 5. Okay. Now part C, here you want to evaluate this about the line x equal to 3. So the graph again is this shape. And, you know, given the information, you're calculating out to x equal 3 anyway, right? So we're going to spin it along this line of x equal to 3. So if you think about it, it's doing that. And you're spinning that solid as such. Now, the radius, it's this. But notice where you're coming from. You're starting off at 3 minus the curve. So capital R, look, the thickness is dy, so this is r of y. This is 3 minus the curve. The curve with respect to y is y squared. So this is 3 minus y squared. Well, that's all you need. And again, this is going out from y equal to 0 to y equal to the square root of 3. So the volume is pi times the integral from 0 to the square root of 3 of the radius to be squared. This is 3 minus y squared to be squared dy. So this is pi times the integral. Simplify that from 0 to the square root of 3. This is 9 minus 6 y squared plus y to the 4th dy. Use blue, I'm sorry. So we integrate. So we have pi we get 9y minus 6y to the 3rd divided by 3. 6 divided by 3 is 2, so minus 2y to the 3rd plus y to the 5th all over 5. Evaluate that from 0 to the square root of 3. So we plug in y to be the square root of 3. And so we have pi times 9 times the square root of 3 minus 2 times the square root of 3 times the square root of 3 times the square root of 3, which is 2 times 3 is 6 times the square root of 3, plus the square root of 3 times the square root of 3, which is 3 times the square root of 3 times the square root of 3, which is 3 times 3 is 9, times the square root of 3. So this is plus 9 times the square root of 3 all over 5. So this gives us 9 minus 6 is 3 times the 5 is 15, and the 15 plus the 9 is 24 pi times the square root of 3 all over 5. Okay. Now part D, let's keep on digging. Part D says to calculate the line, the volume about the line x equal to 6. again, we have this curve stopping at x equal to 3 about the line x equal to 6, not y equal to 6. Okay. Let's come over here. Let's put it right there. This is 3. This is x equal to 6. I'm going to spin it like that. Now, let's use red. So it's a hole here. So the washer method, big R is this. And this R is with respect to y. And it's so thick. This is RY. The thickness runs with respect to y. Again, that's the square root of 3 and 0 down below. So this is, you see, the R of y, it's 6 minus the curve. 6 minus, here the curve is with respect to y, so this is 6 minus y squared. Now little r is 6 minus 3, right? Minus the whole. Little r of y is 6 minus 3, or just 3. So we can calculate this volume. This is pi times the integral from 0 to the square root of 3. It's capital R, it's the washer method, capital R to be squared, 6 minus y squared to be squared, minus little r to be squared, minus 3 squared dy. Let's see if we get it. So this is pi times the integral from 0 to the square root of 3. Simplify all of that. We FOIL this out, so we get 36 minus 12y squared plus y to the 4th minus 9. We're integrating with respect to y. So we have here, simplify that a little bit more. This is pi times the integral from 0 to the square root of 3. And so the 36 minus the 9 is 27 minus 12 y squared plus y to the 4th dy. Now we integrate, and we do not hesitate. So funny. Oh well. So this is 27y minus 12y to the 3rd divided by 3. 12 divided by 3 is 4. So minus 4y to the 3rd plus this y to the 5th all over 5. And we evaluate this from 0 to the square root of 3. I heard a funny sound behind me, but I am not looking back. So if I don't look back, I won't turn into a pillow of salt. Yeah, if I look back, that monster may get me. Anyway, no, let's see. So we plug in everything in. So we get the volume, pi is there. This is 27 times the square root of 3 minus 4 times 3 is 12 times square root of 3 plus 9 times square root of 3 all over 5. That's from evaluating that with the square root of 3. Now when you plug in 0, they all go out. So we get pi times, here this is 15 times the square root of 3 plus 9 times the square root of 3 all over 5. So here we get 75 plus the 9, so that's 84 times the square root of 3 over 5, all times pi. So 84 pi times the square root of 3 all over 5. Okay, good. So that was number 11, and it had a lot of parts there. So hopefully when you look at that on the in WebAssign, you can make something happen. Oh, by the way, maybe you want to know how does this graph look in its totality. Let's see. This is the y-axis, x-axis. We have this part doing that, then it's rotating about the line x equal to 6. So over here we have this image, we have the hole there, right? And that's a hole. It's somewhat of a connector, so it kind of goes all around. And then here there's a something like that. So the emptiness is here, right? It's all connected up there. So try to draw it in to the best of our ability, right? Okay. Let's look at the next problem. Okay, so this problem here, y equal to x squared, y equal to 4x minus x squared. Let's take the first part about the x-axis. Don't ask me why I'm rewriting this because it's written right there, right? But anyway. About the what? About the x-axis. Well, if we look at this second, we need to graph, follow the directions. Factor out of x, get 4 minus x. So the zeros, x equals 0, x equal to 4, would be the x intercepts. The biggest term for this second equation is a negative x squared. So this graph is going downward. It's 0, right? We can go ahead and get the other part in there, if you will. The other graph. The other graph is this parabola. It's the basic parabola. So the part that you want is what I call the moon. I guess I should have drew that yellow, but red moon dripped in blood one night about 2,000 years ago. All right. So now it says you want to rotate this about the x-axis, which would imply then that the radius slice is perpendicular to the x-axis, right? Now notice the thickness of this slice is with respect to the x-axis. So we have delta x for our width. Now we need to determine the points there, or the limits of integration. Right? We set both of the equations equal to find that. So we set x squared equal to 4x minus x squared. And so this gives us 2x squared minus 4x equals to 0. Factor out of 2x. We have left x minus 2 equal to 0. So we get x equal to 0 and x equal to 2, or the points of intersection. And in particularly, that gives us the limits for integration. Here, this is x equal to 2. And this point was x equal to 4 from the intercept, right? Of which we don't need. X equals 0. So we have 0 less than equal to x less than equal to 2. And then notice to get the height, going back to the previous section, the height is the function up above minus the function below. So here the height is, this function above is that parabola that's curving downward. So that's 4x minus x squared. And that's minus the equation down that's below, x squared. Okay. So this gives us 4x minus 2x squared. All right. Very good. So, oh, by the way, what was that? Oh, that's just the radius. Excuse me. And so this is revolving about the so-called the x-axis. Right? So what you're looking at is something that's doing that. Okay. Well, very good. Now we have a problem, and that is we get this hole there. Right? So we got to do some work on all this. So let me work on that. We just call that the height, and let's see if we can perfect it. Okay. So that is, I need the big slice to do this. That's big R. I need the smaller slice to be the hole. So the big one, capital R of X, is this curve here. So that is x squared minus, 4x minus x squared. And then the little radius is the hole that I want to take out, and that's that parabola minus 0. I think the parabola is just x squared. Yes, it is. Right here. If we were just calculating the area, then what I was thinking about initially would have been fine for this right here. But we're doing more than the area. We're calculating the volume with respect to the disk method. So I want to follow that. Things gets a little bit better for the shell method, and what I was hinting around up here was actually going into the shell method, which I think is a little bit easier than this disk method. But anyway, let's continue. So the volume is pi times, we have the limits of integration from 0 to 2, and we need capital R of x there. So it's 4x minus x squared to b squared minus x squared little r of x to b squared dx. So this is pi times the integral from 0 to 2. Simplify all that, FOIL that out, so we get 16x squared minus 8x to the third plus x to the fourth minus x to the fourth. Well, at least some cancels out, I'll tell you. So this is pi times the integral from 0 to 2, 16x squared minus 8x to the third dx. So the volume is pi. We can integrate now. So this is 16x to the third all over 3 minus 8x to the fourth divided by 4. So that's 2x to the fourth. This is evaluated from 0 to 2. So we have pi times 16 times 8 over 3 minus 2 to the fourth is 16 times 2, so that's minus 32. The brain tries to play tricks on us sometimes. Now, then you calculate all of that, and when you do, you get 32 on a calculator, 32 pi all over 3. This is times. It's good stuff. Part B. Part B is very long. See if I can cut around something. I'll try to. So here, this is about the line y equal to 6. So you remember the graph. It was the moon. And in terms of how far we went up here, that point of intersection, x was 2. So if x was 2, then that would give us 4 for the height. And then y equal to 6 is up here. So if you think about it, capital R is this. This is R of x. And then the whole is little r of x. So capital R of x is 6 minus the curve on the bottom, 6 minus x squared. And then little r of x, and this is where we get into a lot of algebra. Little r of x is 6 minus that curve, and that was that 4x minus x squared. 4x minus x squared. So it's minus, parentheses, 4x minus x squared, or 6 minus 4x plus x squared. All right. We're still integrating with from 0 to 2. So the volume is pi times the integral from 0 to 2, capital R of x. This is 6 minus x squared to be squared minus little r of x, which is 6 minus 4x plus x squared to be squared dx. Well, so that's just a little work there on this one. This, before this out, this is 36 minus 12x squared plus x to the 4th, and then minus, it takes some work to FOIL that out. So I did that somewhere. Yes. So let's see. I did that on some paper that I think I threw away. It's not good. Got to FOIL that out. Oh yeah, I remember. Oh, I don't see it. So 6 minus 4x plus x squared times 6 minus 4x plus x squared. So we get 36 minus 24x plus 6x squared. Multiply negative 4 times everything up top. So it's negative 24x plus 16x squared minus 4x to the 3rd. Now x squared times everything up top. So that's 6x squared minus 4x to the 3rd plus x to the 4th. So we get 36 minus 48x plus 28x squared minus 8x to the 3rd plus x to the 4th. So we put all that in there. So it's minus all that. So this is minus 36 plus 48x minus 28x squared plus 8x to the 3rd minus x to the 4th dx. Okay, so the 36's cancel out, and the x to the 4th's cancel out. The volume is pi times the integral from 0 to 2. Let's see. The big guy is the 8x to the 3rd. Let's write him first. The next one would be the minus 12x squared and the minus 28x squared. So that's minus 40x squared. And then the plus 48x dx. So we integrate. So we get 8x to the third, well, to the fourth divided by 4. So that's just 2x to the fourth minus 40x to the third all over 3 plus 24x squared. It's been evaluated from 0 to 2. Okay, so this is pi. Oh, I got an email. 32 minus 40 times 8 all over 3 plus 4 times 24. And if all calculations are correct, which it is, you will get 64 pi over 3. Okay. That's a pretty good one. Yeah, don't you like those kind of problems? Somebody say no. Okay, now, let's see about this one. Here, find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the line y equal to 4. So this problem has a vertical isotope of x equal to -1. So it's a rational equation. So it's doing this. The part that you want goes from when x is equal to 0, which is here, x equal to 3, there, and then y equal to 0, the x-axis. So we're talking about that region inside. But you want to revolve that above it with respect to the line y equal to 4. Okay. So y equal to 4 is there. So we need the big R, right? Remember the thickness is delta x. This is big R. Then we need little r. So little r would be 4 minus the curve. 4 minus and the curve is given by 3 over 1 plus x. And then big R is just 4, or if you're from South Alabama, it would just say 4, right? So we're integrating from 0 to 3. So the volume is pi times the integral from 0 to 3. Capital R to be squared, so that's 4 squared minus, here little r to be squared, 4 minus 3 over 1 plus x to be squared dx. Simplify that. That's pi times the integral from 0 to 3. 16 minus 16. I hope you're not hearing those sound effects. But anyway, this is 14 minus 24 over 1 plus x. It's going to be minus that minus, so it's going to be plus 24 over 1 plus x. And then this is plus 9 over 1 plus x to be squared, but then that minus out there trumps it, so this becomes minus 9 over 1 plus x to be squared dx. So the volume is pi times the 16s cancel out. This is 24 over 1 plus x. I'm going to set this guy up for integration. So minus 9 times 1 plus x to the negative 2 dx. So the first one is just the natural log. So this is pi. Here we get 24 times the natural log, absolute value of 1 plus x. Then we integrate this 1 plus x raised to the negative 2. So that becomes, you can do the u du. If u is 1 plus x, du is just dx, so it's fine. So this is integrating u to the negative 2, so that becomes the 1 plus x to the negative 2 plus 1 divided by negative 2 plus 1. So negative 2 plus 1 is just negative 1. So we have, this is minus 9 times 1 plus x to the negative 2 plus 1 is negative 1, and that's divided by negative 1. That's been again evaluated from 0 to 3. I lost that here, 0 to 3. This is pi 24, the natural log of absolute value of 1 plus x plus 9 all over 1 plus x. That's evaluated from 0 to 3. So the volume is pi 24, the natural log of 4 plus 9 over 4. Then it's minus, plug in x to be 0. The natural log of 1 is 0. So this is minus 9. And this is pi times 24, the natural log of 4. 4 minus 9, negative 36 plus 9 is negative 27 all over 4. That's good. All right, let's see what else we have. Okay, it's the last one. I don't know about you, but my back is hurting. When I'm in the classroom, I'm standing up, so do not like to sit. It's awkward. It feels funny to sit and teach. Anyway, the last one. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the x-axis. Now, this graph, it really acts like the square root of x plus 1. 1 over that, it makes it really small, and it gives it a vertical asymptote. Vertical asymptote, by the way, is negative 1. So the graph of this guy, I don't like that color. So it's doing that, and it's going from x equal to 0, so from here to x equal to 4, and then y equal to 0 is the x-axis. And you want to revolve that about the x-axis. So if I can just put the shape over here, if you will. Can't see my 0 and the 4, and I'm kind of anxious about that. I do not like that. Okay, so it's the radius. Its thickness is with respect to delta x, capital R of x, and it's equal directly to this equation. So R is equal to 1 over the square root of x plus 1. So the volume is equal to pi times the integral from 0 to 4 of the radius to be squared. This is 1 over the square root of x plus 1 all to be squared dx. So that helps us out. So we get the integral from 0 to 4 of just 1 over x plus 1 dx. So it gives us pi times the natural log of the absolute value of x plus 1. That's evaluated from 0 to 4. And so here we have pi times the natural log of 5 minus pi times the natural log of 0, which is just 0. So this is it. And by all means, we want to verify. I don't want to tell you anything that's not correct. Have fun. Thank you.